The Sun, both the giver of life and the potential destroyer of worlds, holds sway over the 8 planets with its gravity, providing Earth with light and heat. For over 4 billion years, our star has played a crucial role in sustaining life on Earth and has captivated human civilization since our earliest ancestors first observed it. Despite its brilliance, the true nature of the Sun's power remains a mystery, with scientists still puzzled by processes in its upper atmosphere. In 2024, NASA will attempt its closest approach to the Sun yet, coming within 5 million miles of its surface. This mission represents a new frontier in heliophysics, venturing into the Sun's upper atmosphere to study every particle, image every eruption, and understand every interaction. Humanity hopes to catch its closest glimpse of the Sun, a cosmic constant in human experience, from early Neanderthals and Aboriginal cultures to the ancient civilizations of Mesopotamia and beyond. Although we perceive the Sun simply as a radiating ball of light, in reality, it is a gigantic, churning nuclear furnace. At its core, hydrogen atoms are fused into helium through the proton-proton chain reaction, powering stars like our Sun. This fusion generates enormous energy that diffuses outward through the Sun's layers, including the radiative zone, where particles take hundreds of thousands to millions of years to rise to the convection zone. Here, energy is transferred outward as plasma cycles, rising and falling in convection patterns until reaching the Sun's visible outer edge, known as the photosphere. The photosphere, which emits most of the Sun's visible light, is not a solid surface. Instead, it is the lower boundary of the Sun's superheated atmosphere, or corona. Here, plasma particles are swept up in magnetic fields, forming explosive arcs that contribute to the Sun's corona, a region of high temperatures and magnetic storms. Despite being farther from the core, the corona is millions of degrees hotter than the Sun's surface, an unsolved mystery known as the coronal heating problem. In the Sun's atmosphere, particles can escape once they reach a point known as the Alfvén critical surface, beyond which they shoot into space as the solar wind. This solar wind creates the heliosphere, an extensive bubble surrounding our solar system, where the conditions dictate the space weather affecting Earth. Solar activity fluctuates on an 11-year cycle, from a calm solar minimum to a stormy solar maximum, marked by tangled magnetic fields, sunspots, and intense solar flares. These solar flares release high-energy radiation that can interfere with Earth's satellite systems and electronic devices. When combined with coronal mass ejections, large clouds of charged particles can cause geomagnetic storms, disrupting power grids and generating brilliant auroras. For example, in 1989, a massive coronal mass ejection disrupted power in Quebec, Canada, in an event known as the Day the Sun Brought Darkness. The largest geomagnetic storm, the Carrington event of 1859, similarly knocked out telegraph systems worldwide. If a similar event struck today, the consequences would be even more severe. In 2012, a Carrington-sized ejection narrowly missed Earth. Observed by NASA's Stereo A satellite, it underscored the potential disruption a large solar storm could cause to modern infrastructure. Various missions have since studied solar phenomena, including the Solar and Heliospheric Observatory, SOHO, and the Solar Dynamics Observatory, SDO, both providing invaluable data on solar activity. NASA's Parker Solar Probe, launched in 2018, has brought us closer to understanding the Sun than ever before. Equipped with state-of-the-art technology, Parker has approached closer and faster than any spacecraft in history. Named after solar physicist Dr. Eugene Parker, it studies the Sun's magnetic field, imaging the coronal plasma and tracing solar wind particles to their origins. In April 2021, Parker breached the Alphane surface, entering the corona and capturing detailed images of coronal plasma streams. Its findings on magnetic anomalies, called switchbacks, have revealed new insights into solar wind dynamics, helping us unravel the mysteries of our sun's atmosphere.